Greenland Ice Sheet Subglacial Flood, 2025 study reveals Arctic hydrofracture discovery. The eruption of a subglacial flood from the Greenland Ice Sheet. Introduction. In the last 30 years, the Greenland Ice Sheet has experienced a staggering loss of approximately 169 billion tons of ice each year, which has contributed around 14 millimeters to the global rise in sea levels. This alarming trend is primarily attributed to surface mass balance processes, which account for nearly half of this ice loss, driven mainly by increased melting and runoff from the ice surface. As the Arctic continues to warm, projections indicate that the extent and intensity of surface melting in Greenland will escalate, resulting in even greater losses of ice mass and an increase in liquid water both on and beneath the ice sheet. The importance of meltwater movement. Understanding how meltwater travels from its source to the ocean is crucial for predicting Greenland's future role in sea level rise and its broader effects on the Arctic ecosystem. It is well known that meltwater generated at the surface of the ice sheet can infiltrate to the base through features like moulins and crevasses. Observational studies, particularly in southwestern Greenland, have demonstrated that the subglacial hydrological system reacts swiftly to water input, and fluctuations in subglacial water flow significantly influence the dynamics of the overlying ice. It is essential to identify both the modes, whether continuous or episodic, and the pathways, whether surface, endglacial or subglacial, of water drainage, as well as how much meltwater is stored during its journey. These elements play a vital role in various processes including ice dynamics, thermodynamics, interactions between ice and ocean, fjord circulation, primary productivity, and the transfer of sediments and nutrients to the ocean. Subglacial lakes, a new discovery. One of the more recently identified yet poorly understood aspects of Greenland's subglacial hydrological system is its network of active subglacial lakes. These lakes are mainly replenished by surface meltwater that seeps down to the base of the ice sheet and can discharge large volumes of water through the subglacial system when they drain, thereby altering both the morphology of the system and the dynamics of the surrounding ice. However, detailed observations of subglacial lake drainage events in Greenland remain scarce, and our understanding of their causes and effects is still limited. Furthermore, the thermal conditions at the base of the ice sheet, which are crucial for understanding subglacial water distribution and dynamics, remain uncertain across a significant portion of the ice sheet. In light of the increased runoff expected in the 21st century and the anticipated rise in the frequency and extent of subglacial lake drainage, the impacts of these poorly understood events on the ice sheet are still unclear. This study presents observations of a destructive mode of subglacial lake drainage in Greenland and analyzes its effects on the surrounding ice sheet. Observations of subglacial lake drainage in North Greenland. Utilizing high-resolution Arctic DEM digital surface models and satellite imagery, we identified and monitored a previously undetected subglacial lake in northern Greenland near the marine terminating Harder Glacier. During a 10-day period in the summer of 2014, a 2-kilometer square area of the ice surface experienced an 85-meter drop in elevation, creating a deep collapse basin. This rapid deflation occurred approximately 25 kilometers inland on slow-moving ice adjacent to the main glacier, shortly after the seasonal peak in runoff. Prior to this event, the surface of the basin had been rising, forming a dome about 10 to 15 meters high above the surrounding ice. After the collapse in 2014, the ice within the basin began to uplift again, but it subsided by about 10 meters between 2017 and 2019. This dynamic behavior is interpreted as the surface manifestation of an active subglacial lake, akin to those previously documented in Greenland and Antarctica. Estimating water discharge. Assuming that the volume of water released by the subglacial lake corresponds to the volume displaced by the newly formed surface feature, we estimate that approximately 90 million cubic meters of water drained from the lake during the 10-day period. Concurrently, a nearby superglacial lake also drained, indicating a direct connection between the surface and basal hydrological systems. Modeling of surface and basal melting upstream suggests that the subglacial lake was primarily fed by locally sourced surface meltwater, with over 99% of the water generated within its catchment coming from surface melt and 73% of all meltwater produced within 2 kilometers of the collapse basin itself. During the drainage period, the lake discharged water at an average rate of 100 meter cubed per second, with peak discharges likely much higher if the drainage occurred over a shorter time frame. This water flux was 2 orders of magnitude greater than that from a similarly sized Antarctic lake and represents one of the largest recorded events beneath the Greenland Ice Sheet to date. Notably, the estimated discharge rate indicated a 30-fold increase in the daily meltwater runoff from the entire Harder Glacier catchment at that time, suggesting that the lake drainage significantly disturbed the downstream subglacial system. Surface outburst dynamics. Theoretical models and observations of lake drainage indicate that floodwater is typically routed subglacially, following gradients in hydraulic potential. Thus, subglacial floods in Greenland are generally part of a larger unidirectional hydrological system, where surface meltwater flows from the surface to the bed and eventually to the ocean. However, we have identified a contrasting drainage pathway in this instance. About 1 kilometer downstream from the collapse basin, a new fracture zone appeared in the ice surface, characterized by crevasses and uprooted ice blocks, reaching a combined height of 40 meters. Downstream of this fracture zone, a 6 square kilometer area of the ice surface was scoured clean, indicating that a significant volume of water surged through the ice at this location and flooded across the surface. A hydraulic potential difference between the lake and the fracture site suggests that the floodwater had enough hydraulic head to breach the surface at the fracture site. Additionally, estimates of the longitudinal strain rate reveal a shift from compressional to extensional flow at the fracture site, which may have facilitated fracturing through the ice column. Historical context of surface features. Analysis of satellite imagery over the past 36 years shows that the oval-shaped surface feature above the subglacial lake has been present since at least 1985. Within this time frame, we identified a single drainage event prior to 2014, which occurred between June 21st and August 1st, 1990, when the ice was over 10 meters thicker. Unlike the 2014 event, the 1990 drainage did not result in downstream surface fracturing, indicating that the floodwater flowed entirely along the basal interface. Therefore, we conclude that the 2014 surface outburst was unprecedented in the observational record. Impacts of the 2014 outburst. The area of ice that was scoured by the flood ended abruptly after several kilometers, at a location where a superglacial lake also drained. The lack of surface scouring beyond this point suggests that the floodwater, after erupting through the ice and flowing across the surface, re-entered the glacial and subglacial systems at this site, continuing its flow beneath the main trunk of the Harder Glacier. The simultaneous drainage of both the subglacial and surface lakes implies that the surface flood may have triggered the latter, likely through hydrofracture at the lake bed. Analysis of the basal hydropotential indicates that the floodwater was subsequently routed beneath the Harder Glacier, exiting at the glacier's main northern terminus. During the same 10-day period, the glacier's terminus experienced a significant calving event, with an ice front retreat of 500 to 600 meters, marking the 7th largest event in the past 32 years. While the direct connection to the lake outburst remains uncertain, these observations align with the theory that a rapid influx of water could have influenced the stress regime at the ice front or enhanced ocean-driven melting and undercutting. Inclusion. Our findings indicate that the drainage of the lake caused a significant disturbance to the hydrological system of the ice sheet. To assess the potential impacts on downstream glacier dynamics, we generated 5,800 maps of ice velocity from 1985 to 2020. These maps reveal that the dynamics of the Harder Glacier exhibit a clear seasonal cycle. superimposed on a longer-term acceleration since 2014 to 2015. The relationship between lake drainage and the acceleration observed in 2014 remains ambiguous, given the limited data available prior to 2013 and the multitude of factors influencing the flow of marine terminating glaciers. However, in the weeks following the outburst flood, we observed a notable short-term disturbance in the glacier's dynamics, with a rapid deceleration of 80 meters per year, measured approximately 5 kilometers inland from the ice front. While late summer deceleration is typical, the 2014 deceleration was approximately 300% greater than usual, resulting in a 63% loss of peak summer velocity by September 12, compared to an average reduction of 37% in other years. These observations support the theory that a sudden influx of floodwater enhanced the efficiency of the subglacial system, reducing basal water pressures and ultimately slowing ice movement. This mechanism, well documented for supraglacial lake drainage, appears to also affect fast-flowing marine terminating glaciers. Future research directions. The implications of this destructive and poorly understood subglacial flood process necessitate a deeper understanding of the physical characteristics of the system, particularly the basal conditions immediately downstream of the lake, which influence the initiation, propagation, and outburst of floods. While our observations suggest that upward propagating hydrofracture occurred at the outburst site, it remains unclear whether the drainage of the subglacial lake was also initiated by hydrofracture along the basal interface, or through a process associated with temperate ice masses. Further research is required to test these hypotheses and enhance our understanding of the role of hydrofracture within the context of ice sheet dynamics. 90 billion liters of meltwater burst through Greenland ice sheet in unseen 2014 flood. A stunning discovery. 90 billion liters of water erupt from Greenland's ice sheet, and few realized it. In a remarkable event that went largely unnoticed, a massive accumulation of meltwater beneath Greenland's ice sheet in 2014 led to a flood so powerful that it surged upward through thick layers of solid ice, fracturing the surface and releasing water into the atmosphere. This unprecedented occurrence marks the first time scientists have documented such a phenomenon in Greenland, providing crucial insights into the future transformations of the region as the ice sheet continues to diminish and contribute to rising sea levels. This incident underscores the immense power and potential destructiveness of meltwater that resides beneath the ice sheet. The discovery of subglacial lakes beneath the Greenland ice sheet is relatively new, and our study reveals that there is still much to learn about their development and the effects they have on the ice sheet system, states glaciologist Jade Bowling from Lancaster University in the UK. Our findings highlight the urgent need to understand how frequently these lakes drain, and importantly, the implications this has for the surrounding ice sheet. Related insight. Scientists have suggested the existence of a mysterious dark river that may flow for 1,000 kilometers beneath Greenland, further complicating our understanding of this icy landscape. Greenland's ice sheet, a colossal mass of ice covering most of the island, reaches a maximum thickness of over 3 kilometers, 1.9 miles. This frozen expanse contains a staggering amount of water. If it were to melt completely, global sea levels could rise by approximately 7.4 meters, 24 feet. Recent advancements in technology have allowed scientists to explore what lies beneath the ice. Using aircraft equipped with radar, researchers have begun to map the complex and dynamic environment hidden below. These observations reveal that liquid lakes are not only common beneath the ice sheet, but also fluctuate with meltwater, sometimes causing the ice to bulge upward in a phenomenon known as water blisters. The discovery of a flood powerful enough to fracture the ice is unprecedented. Bowling and her team uncovered evidence of this extraordinary event by analyzing satellite data from 2014. During a 10-day period from late July to early August, they observed a dramatic drop in elevation of an area spanning 2 square kilometers, which fell by an astonishing 85 meters, the equivalent height of a medium-sized skyscraper. Before this collapse, the area had been rising by about 10 to 15 meters as water accumulated and pushed it upward into a dome shape. The sudden drainage of approximately 90 million cubic meters of water caused this dramatic drop. About 1 kilometer downstream from the basin, researchers noted further anomalies. A large section of the ice had become heavily fractured, with ice boulders reaching heights of up to 25 meters deposited on the surface. Additionally, a 6 square kilometer area of the ice sheet was found to be scoured clean. Initially, we were taken aback by these findings, as they were so unexpected that we questioned the integrity of our data, Bowling explains. However, as we delved deeper into our analysis, it became evident that we were witnessing the aftermath of a significant flood of water escaping from beneath the ice. The fracture zone downstream from the basin is where the water burst forth, gushing out and washing away a vast area as it flowed across the surface. While previous studies have indicated that meltwater can move beneath the ice, this is the first documented instance of it breaking through the ice layer. As Greenland continues to experience rapid melting, this information is vital for understanding the implications of these changes. Our study has revealed surprising insights into how ice sheets respond to extreme inputs of surface meltwater, emphasizing the necessity of comprehending the complex hydrological systems of the ice sheet, both now and in the future, says glaciologist Amber Leeson from Lancaster University. Given the significant influence that subglacial hydrology has on the dynamics of the ice sheet, it is crucial that we enhance our understanding of these hidden and poorly understood hydrological processes, and satellite observations are essential for this endeavor. This groundbreaking research has been published in Nature Geoscience.